Hello class, this is our lecture for our enzyme kinetics or introduction about the enzyme kinetics because I am not going to discuss this in a comprehensive manner. I'll just provide you the surface of about this topic of this enzyme kinetics. So what are we going to discuss? Siyempre, when you say enzyme kinetics, ang pinakasikat na maririnig natin dito is the Michaelis-Menten equation. Ayan, so ito yung pinaka-main topic natin sa ating discussion nito, the Michaelis-Menten equation. And then we will discuss the Lineweaver-Burke plot, which is the reciprocal form of the Michaelis-Menten equation. And then we will impose some inhibitors. We will discuss the effects of the types of inhibitors in the Michaelis-Menten equation or in the Lineweaver-Burke plot or equation natin. And then after that, we will discuss the allosteric regulation, which is a both activator and inhibitor, which doesn't obey the Michaelis-Menten equation. And I just provide you one example of this, which is the phosphorylation. Okay, so let's start with the Michaelis-Menten equation. What is the Michaelis-Menten equation? Ayan. Okay, the Michaelis-Menten equation is the kinetic model to describe the aspects of the enzyme's behavior. Kasi nga, each enzyme has a Michaelis-Menten constant or Km. So what is Km? Di-discuss natin ito mamaya. So paano ba na-derive yun? Okay, since we are talking about the enzymes, which is defined catalyzes, its function is catalyzes the chemical reactions of the substrate specifically or in general is yung sa ating metabolism natin. So the role of the enzyme is to catalyze the substrate to form its products. Okay? Pero we have to consider yung numerical value, kung gaano kabilis proceed yung reactions natin. So this is the typical chemical equation for the enzyme and substrate reaction in the system natin. Okay? So we have the substrate binded to the active site of our enzyme to form a enzyme substrate complex, by which the K here is the rate of the formation of enzyme substrate complex, rate constant, kung paano kabilis mag-proceed yun. And it is a constant value. And then after the enzyme substrate, as illustrated in the introduction in our enzymes lecture, it will form a product. And then the enzyme will retain its shape. Pero ma-discuss natin yan na hindi siya mariretain, but rather we are mag-inhibit or mag-regulate niya. We will discuss this in the further topic. And take note, guys, that the enzyme plus substrate and enzyme substrate reaction is a reversible reaction. It is assumed in the Michaelis-Menten equation. So in-assume nila yan. That is the two conditions. One of the conditions in order to establish the Michaelis-Menten equation. So this is the typical equation. So after that, magkakaroon tayo ng simultaneous derivation here by which the Km or the Michaelis-Menten constant is equals to K-1 or the reverse reaction of the enzyme substrate complex to back to its enzyme plus substrate. So paghihiwalay natin yung enzyme substrate, yun yung K-1, the rate of the breakdown of the enzyme and substrate, plus the K2 for the formation of the product from enzyme and substrate all over the K1. So the K1 here is the formation of the enzyme plus substrate to enzyme substrate complex. So this is the Km, the Michaelis-Menten constant. And then magkaroon tayo ng simultaneous derivation. Okay? Ito yung may yield natin. This is the equation. This is the famous Michaelis-Menten equation where B sub O is the rate of the reaction or the enzyme, and then the Bmax is the maximum rate of reaction or velocity na tinatawag nila, the reactions proceeds. And then this variable here is the concentration of the substrate, and then the Km is the Michaelis-Menten constant. So ano-ano ba? Paano ba na-derive yung equations na yan? Siyempre, hindi ko yan i-discuss dito kasi mapapahaba yung discussion natin. So, papakita ko na lang if may mag-request, sige, I will just wait for you. I-derive siya. Pero buod na lecture niya. Kung may mag-request naman. Okay, so this equation is established when two conditions are assumed. So ano ba yun? First, yung ating equilibrium. It is assumed that the isolation and dissociation of substrate and enzyme is assumed to be a rapid equilibrium. And then, yung KEQ type nyon is, tawag nun, is Ks, or the dissociation constant of the enzyme and substrate. And then the other assumption that the Michaelis-Menten assumed is the steady state. So what is the steady state? Ang in-assume nyan is the rate of the formation of the enzyme substrate and its product is equal. So, ayan na, after that equation, actually mahaba yung equation na yan, na kung saan is kukunin siya from manggagaling dito, here, dito siya manggagaling. So, it is a chemical kinetics. Sa field ng chemical kinetics yon to form this Michaelis-Menten equation. So, ayan yung magiging form niya through simultaneous derivation. So, ito na yung formula ng Michaelis-Menten equation. Yan. Ayan. So, ano ba yung Km na sinasabi natin? What is the definition of Km, sir? Bakit siya nag-appear dito? Ano pa yan? Kasi ito, in terms of molarity, this one here is molarity per second. Pero ano ba naman itong Km na to? Okay? Ito yung, it is the measure of the affinity of the enzyme for its substrate. So, kung gaano kakapit yung enzyme dun sa may substrate natin. Or it is also known as the binding constant. Kung gaano kalakas yung kapit, na kung saan sila yung magde-determine, malaking factor yan to determine the rate of the reaction. So, and by the way, since the Michaelis-Menten equation is a first order kinetics, kasi nga sa kinetics natin, we have zero order, we have first order, second order. And the Michaelis-Menten equation is a first order reaction when, tandaan niyo, in two conditions, okay? So it is a first order reaction. And the Km values for each enzyme, as I say, is always a constant value. So you don't need to calculate for them. Kasi, ayan na, meron silang values dito. And it's a table. Actually, masyadong madami. This is just a typical example of it. Ayan. So, isa-substitute na lang siya sa equation in order to determine the rate of the reaction it will proceed. Yeah, so the Km, so ito na yan, the catalase is 2.5 instead of -2, and so on and so forth. And then the catalytic efficiency of it is this one is Kcat. Ayan, so this one here is the ratio of catalytic efficiency here. Saan ba yun? Madidiscuss ko yun mamaya. Ayan. So that's the Km. So we have to go on since we're talking about the Michaelis-Menten equation. Ano ba ang graphical representation niya? Okay? Hindi ko nababasahin to. Let's just let's say that the substrate concentration is equal to the Michaelis-Menten constant. Ganito yung magiging itsura niya. Na kung saan, for us to determine the velocity of the reaction, i-determine nyo lang yung maximum velocity divided by 2, and you will determine the V sub O, or the rate of the reaction. By which, syempre, i-assume natin dito that the Michaelis-Menten constant is equal to the concentration of the substrate. Okay? So ayan, this is just another typical graph for the reaction progress of the enzyme interacting with the substrate. Okay? Or the substrate at the enzyme's active site. So yun yung ating Michaelis-Menten equation. Now, yung Michaelis-Menten equation natin can be plotted linearly for us to determine the numerical value para nga makuha natin yung sinasabi natin y is equals to mx plus p, or linear equation. So, ang purpose nun is to have a series of data. So we'll just plot it in the graph and determine whatever variable you determine, or the given velocity and the required concentration of the enzyme. So, makuha yun. So, for the Lineweaver-Burke is actually a double reciprocal plot of the Michaelis-Menten equation. And ikuha na natin dito, let's cut to the chase. Ayan. So, paano ba natin na-determine yan? Sige, isulat natin guys. Sige, isulat natin dito para mas maintindihan natin ating pa natin. So, this one here is the equation for the graph here. The Michaelis-Menten equation, di ba, as equation of V sub O is equals to V max times the concentration of S all over the concentration of the substrate plus the Km. Ngayon, ang gagawin natin dito, guys, is reciprocal both sides. So, ano bang ibig sabihin ng reciprocal? That is 1 over V sub O is equals to S, Kasi babalik na rin na natin to eh. Plus Km all over Vmax plus, times the concentration of the substrate. By which pwede nating i-equal natin dito, ayan. So paghiwalayin natin, S all over Vmax all over concentration of S plus the K sub M all over the Vmax all over the substrate concentration all over V sub O. And then kung mapapansin niyo, same variable sila. So magkakaroon ng cancellation here. Then 1 over V sub O is equals to 1 all over Vmax plus the Km all over Vmax. Ayan, so imamanipulate ko na dito. Ayan, so 1 all over S here. So ano bang ibig sabihin niyan? So this one here, magkakaroon tayo ng form na y is equals to mx plus b, where y is the b sub o, reciprocal of the 1 b sub o, is equals to here, this one here is the b, or the y-intercept, plus the m is the term, this one, the term here, the km over vmax, and the x term is the 1 all over substrate concentration. So if you are going to plot this in a graph, ganito ang kuha natin. This is the y-axis, 1 all over v sub o, and the x-axis is 1 all over S concentration. And then you will yield a linear equation here. A linear equation, let's suppose that the enzyme follows a Michaelis-Menten equation. The slope here will be the Km all over Vmax. So if you're familiar with the linear regression analysis, you can easily determine the Vmax of the enzymes given the data follow na kung given yung data nito at tsaka nito. So, the double reciprocal fact. So, mas mapapadali yung equation natin dito if data type yung gagawin natin. Okay? So, that's the Lineweaver-Burk plot. Ayan. So, ayan. So, nandito lang pala yun here. Ayan. Km over Vmax. This is just the graph. And then, let's go on to the inhibitors. So, sir, why do we need to tackle the inhibitors? Kasi nga, di ba, as discussed dun sa may ating natin sa ating introduction to enzyme lecture, that the inhibitors affects the rate or the efficiency of the enzyme to catalyze as a substrate. So, we have 4 types of inhibitor here. The competitive inhibitor, the non-competitive inhibitor, uncompetitive, and mixed inhibition here. Okay, so, sir, did it affect the rate of reaction? Of course, yes. Kasi nga, sila yung mga inhibitors ng enzymes natin. So, it will affect the Lineweaver-Burk plot and or the Michaelis-Menten equation. And then, magkaaroon tayo ng variation sa mga graphs natin. So, simulan natin sa may competitive inhibitions. So, ang analogy nito sa ating competitive inhibition is yung ating here, this is a graphical representation here. Ayan, so this one here, ayan yung equation ng graph. But let's suppose we have the substrate box here and then the inhibition box here. And this one here is the enzymes. So, depende yun kung paano yung magiging pasok nila. But ang point out dito here that the substrate and the inhibitor will go on to the active site of our enzyme. Doon sila parehas napapasok. Na kung saan mapapansin ninyo, the binding efficiency or the Ki, ayan, will affect doon sa may enzyme natin to form an enzyme inhibitor complex plus substrate and then enzyme substrate complex to form a product. So ano bang magiging effect niyan sa may equation natin? Ganito yung magiging effect niya. This is a typical example of a inhibitor. Ayan, this is the equation. So I'll not dito, hindi ko na siya i-discuss thoroughly. Ang interest natin dito is the equation. So mapapansin niyo, this one here, mag-i-introduce tayo ng alpha doon sa may ating Michaelis-Menten equation. By which the alpha is equals to 1 plus concentration of inhibitor all over Ki. Whereas the Ki is equals to the concentration of the enzyme. Okay, para mas maging pa natin, let's expand our equation here. So I hope you can follow this one here. So ang ating magiging bagong Michaelis-Menten equation when competitive inhibitor kapag meron tayong competitive inhibitor will be Vmax all over times S all over alpha Km plus concentration of the substrate. Whereas the alpha is equals to 1 plus concentration of the inhibitor all over Ki. Whereas the Ki naman daw is equals to concentration of the enzyme times the concentration of the substrate here, and then concentration of the enzyme and inhibitor complex. So simultaneous naman yan. So meron na naman sa problems, usually, given naman yung concentration ng enzymes, given yung concentration ng I, and then given din yung concentration ng Ki. So Ki, substitute nyo lang yung values dito. And ayan, once na may values na yan, syempre, magkakaroon din ng values dito since it is an I. Ayan. And magkakaroon tayo ng values here, values din dito, and you will have the result for the alpha here. Kung saan, ayan nga, i-impose mo ngayon to dito sa may alpha. If you want to expand further this equation, syempre, okay, I'll just go natin. So, this is just a scratch paper. Okay, so Ki will be E, concentration E times concentration of I, times concentration of the EI here. Ayan, so cancel yung I. So, magiging ko natin dito is Vmax times concentration of S here, over the alpha. So that is 1 plus concentration of the enzyme substrate, enzyme inhibitor, and then I here times the Km plus concentration of S. So ganyan yung magiging bagong equation natin. So pasensya na sa may handwriting skills ko. I hope you get the equation here. Ayan. So that is the typical equation for that, for the competitive inhibitor of our enzymes. Now, ano bang magiging epekto nito sa graph natin? Kung mapapansin niyo in the Lineweaver-Burke plot, nagbabago yung natin. As the alpha, ayan, so alpha is 1, syempre no inhibitor. Ayan. Mapapansin niyo when inhibitor is present, nagiging mas steep yung natin or mas tumataas yung slope ng ating plot, Lineweaver-Burke plot, which gives a variation, ayan. But yung indeterminate here kasi nga establish naman na equation dito. But the point here is that the here is nagbabago yung slope natin as the concentration of the inhibitor increases. So, isa lang naman yung y-intercept nila. So, ayan. So, intercepts here. And then next naman natin is the non-competitive inhibitor. Okay. Non-competitive inhibitor binds to the distal of the active site. So, affects enzyme rate, not the affinity. Okay, ganito yung mangyayari dito. Sa may ating non-competitive inhibition naman, guys, I have an illustration here. Wait lang. Yan, here. So, the non-competitive inhibition will bind to the enzyme and to the enzyme substrate complex. So, ganun ang magiging kanya. Ito, ayan. So, we will form a enzyme inhibitor complex and enzyme substrate inhibitor. So, ano ba magiging kanya? Ano bang illustration ng ating non-competitive inhibition? Okay, ang nito guys is here. So, ang magiging nito, ayan. So, mangyayari naman dito sa ating non-competitive inhibition is just suppose this is our substrate here. Let's discard that. Then this one here is the enzyme here, and then this is our inhibitor. So yung sa may competitive is siya sa may active side sumusuot. Dito man, pwede sa may likod or kahit saan ng enzymes ang atakihin niya. Ang magiging result ng doon is yung ating active site natin will change its form. So, ibig sabihin nun, the enzyme substrate will lose its affinity to the So, magbabago yung natin. Yung affinity ng substrate dun sa may enzyme, thus affecting the efficiency of the reaction or the rate of the reactions natin. Okay, so how it will affect, yung paano ba maapektuhan yung ating Lineweaver-Burke equation or the reciprocal equation of our Michaelis-Menten equation. So, ganito yung mangyayari. Walang graph. Okay, I think that will be the assignment. Okay, that third one here is the uncompetitive inhibitor. Binds covalently in the transition state of our enzymes. Okay, kung yung non-competitive inhibition natin, competitive inhibition pala is nagbabind doon siya sa may enzyme, doon sa may active site na enzyme. Yun naman ang competitive inhibition after the enzyme binds to this, after the substrate binded to the active site of the enzyme. Tsaka ngayon papasok yung ating uncompetitive inhibitors. Now, saan will affect the reaction here? The Lineweaver-Burke plot or the efficiency of the enzyme substrate reaction. And ganito yung magiging itsura ng graph niya na kung saan mapapansin ninyo, parehas lang naman yung magiging value ng slope natin for this one. Siyempre, ayan, hindi naman nagbabago slope. But as the concentration of the inhibitor increases, mapapansin niyo that the B sub O or the reciprocal of the velocity of the rate of the reaction of the enzyme substrate reaction will decreases. Ayan. So, mapapansin niyo, that's the efficiency here. Ayan. So, nagdi-decrease siya. So, since take note guys that ito ay reciprocal form. So, in terms of value of the reciprocal of the V sub O, syempre mag-increase siya. But when you get the actual numerical value of the inhibited ends, V sub O is mas mababa yung may yield ninyong results or value. Ayan. So, next naman natin is the mixed inhibition binds in enzyme or enzyme substrate or enzyme. So, pwedeng both din. But ang difference nito is dun sa ating mixed inhibition, the enzyme inhibitor and the enzyme substrate inhibitor complex will not interact with each other. Dito kasi sa may non-competitive, kung mapapansin niyo, is nagkakaroon sila ng interaction dito. Samantalang sa may mixed inhibition is walang interaction na mangyayari. So, ganito naman yung magiging graph ng ating Lineweaver-Burke equation. And as you can see here, naapektuhan din yung rate ng reaction kasi nga tumataas yung ating Y value in our plot, our Lineweaver-Burke plot. Na kung saan naman is, syempre, they have its own equation here. And ito nga yun. Ayan. So, I'll not discuss this further. You'll do the derivation in this part. I-follow nyo lang yung naging style ng pag-derive ko kanina to get its simplified form or expanded form of the equation. Na kung saan makapansin ninyo, the alpha is multiplied to the km and the alpha prime is multiplied by the s. Na kung saan, ayan nga, affecting the efficiency of the enzyme. Ayan, so here, these are the difference of the competitive, the non-competitive, and the uncompetitive inhibition here. Ayan. So, okay. Ayan, so Vmax, these are some numerical definition of it. Ayan. Next natin is the other type of inhibitors. Dito na nga papasok yung ating allosteric regulation. Okay. And ang example lang na itatakal natin dito is just the phosphorylation. So, sa ating allosteric regulation, guys, okay, kung naman kasi, yung enzyme natin, hindi naman siya basta tanggap ng substrate. And i-convert niya into products. Kumbaga, hindi siya laging active. It needs time to rest or I have no idea. If you have idea of this, kindly comment it in the comment section. Ayan. So, para makapag-regulate yung catalytic activities natin. So, mapapansin niyo yung ating allosteric regulation or inhibitions dun sa ating mga metabolic processes in response to the changes in the environment. Okay, they have both inhibitors and effectors. Kung mga sa may kuha natin, to the factory analogy, hindi ka pwedeng produce. You need to stop para hindi magkaroon ng overproduction. Parang sa katawan natin, you need time to rest. So, paano ba mangyayari yon? And dun sa may allosteric regulation natin, doesn't follow a mechanism and kinetics, but instead, a heel plot for the effects, the inhibitor and activator effects natin. So, ayan. So, there are two ways of allosteric regulation. Kinaan natin, controls enzyme availability. So, it's either synthesis of the enzyme or generation. And control enzyme activity na kung saan it alters the binding site, the active site of the enzymes or the binding affinity in order to it to control. Yun nga. And I will just provide you an example dito. Ayan. So, ang common example na ikuan ko dito is the phosphorylation in the photosynthesis. Okay, meron tayong kinases for the enzyme responsible for the phosphorylation and phosphatases for the dephosphorylation. Okay, ngayon, ang mangyayari dito, the enzymes here, okay, by this enzyme, ang mangyayari dito is the on and off switch. Okay. Ang example nito, ayan, kung mapapansin niyo, for the production of the ATP to ADP to the phosphatase, ayan. So, the PEP carboxylase is the inactive day form na makikita ninyo sa may CAM and C4 plants. Na kung saan, ang example natin dito is yung ating mga CAM plants nga. Okay. Okay, the PEP carboxylase, the kinase, ayan, after the kinase binded the enzyme, this one here, turo the kinase enzyme. So, mag-form tayo ng PEP carboxylate, which is the active site form. Na kung saan, ito na nga, siya ay insensitive doon sa may malate natin. So, the malate will not inhibit the PEP carboxylase form. So, magkakaroon tayo ng proceed of reaction. Pero if you want to switch off the reaction, yun nga, meron tayong phosphatase enzyme na kung saan PEP carboxylase, ngayon dito na ngayon papasok yung ating malate to inhibit the enzyme natin para mabawasan yung efficiency niya. Okay? So this is just a typical example of the allosteric regulation. Ito ay kung natin dito is I think this is part of the Calvin cycle or carbon fixation process that happened in the CAM plants natin. Okay? So, ayan. Well, just kung natin. So, during the day here, ayan yung mangyayari naman, phosphatase, so simultaneous reaction. And then, ayan. So, another concepts, additional concepts for the kung natin sa ating phosphorylation. Yan. So, I'll just leave this problem to you all dito. And I forgot to mention, I think, the other equation for the catalytic efficiency of the enzymes. Ayan. So, this is the sample problem here. Ayan. So, another ko natin. So, you have to solve this problem using the Michaelis-Menten equation. Or, meron din tayong other form, the Michaelis-Menten here. Okay, so let's solve this problem. Okay. Let's solve this problem here, the catalytic efficiency. Okay. Okay. Now, let's solve this one problem here for the sake of, yan. Okay. An enzyme is discovered that catalyzes the chemical reaction SAD and equilibrium reaction HAPI. A team of motivated researchers sets out to study the enzyme, which they call HAPiase. They find out that the K-cut or the turnover number for HAPiase is 600 per second. They carry out several experiments. Ayan, so when the enzyme total concentration of the enzyme is equals to 20 nanometer, and SAD, concentration of SAD substrate is equals to 40 micromolar, the reaction velocity is visible is 9.6 micromolar per second. Calculate the Km for the substrate SAD. So, paano ba natin i-calculate? Yeah. First and foremost here. Okay. So, let's have this equation, dV sub O here is equals to Vmax times the concentration of the substrate here over concentration of the substrate plus the Michaelis-Menten equation. Hinahanap kasi natin yung Michaelis-Menten equation. Now, I'm going to introduce you the K-cut or the turnover number, which I forgot to mention and included in this PowerPoint, which is ang equation niya is the Vmax all over the total concentration of the substrate here. Okay, now magkakaroon tayo ng criss-cross multiplication, we will yield that Vmax is equals to Kcat times ET here, by which the Vmax, ayan, sa substitute na natin siya dito. So we will have the equation, we have V sub O equals to Kcat times concentration of ET times concentration of the substrate all over concentration of S plus Km. So, syempre, direct substitution na lang gamit dito. So, Kcat, nasan ba Kcat natin? Ayan, no, 600. So, 600 per second negative times the total concentration of the enzyme. So, convert natin to into micrometer. So, we will have a 20 times 10 raised to negative 3 micromolar times the substrate concentration. Ano ba yung substrate natin? The SAD. So that will be 40 micrometer here. All over the concentration of the substrate. So that will be 40, ayan, 40 micromolar plus Km. Ayan. Km is equals to, ilan yung V sub O natin? That is 9.6 micromolar per second. So, dito tayo magkakaroon ng mahaba-habang equation. So, kayong bahala ng technique dyan. But the goal here, guys, is to solve this Km. So, I'll use this ko na lang. So, 9.6 times micromolar per second times, ayan, times 40. Ayan. Ikuan ko na yan, the common factor yata methods may algebra na yun. Basta ganyan. So, 40 micromolar plus the Km is equals to, ayan, so let's solve this ko natin dito. Let's solve this value here. Forgot to bring my calculator. Okay, sorry for that. And our value for this is 48 micromolar. Okay, this will be squared kasi pinag-multiply natin to all over S kasi S negative ba here. Now, dito, magkaroon tayo ng equation here and here. Ayan. So, magkaroon na dito ng direct computation here. So, 9.6. 9.6 times 40, that would be 384. So, 384 micromolar per second here. Wait lang, I'll detect some error. Okay, guys, I detect some error here. This is not supposed to be 48, but rather a 480. Ayan, so sorry for that mistake. And so we have micromolar squared here all over S plus Km equals to 480 micromolar squared all over S. Syempre, transpose mo to other side. Syempre, magiging negative yan. And ayan, we will have the value for it. So 480 just minus 384. Remember, nagkaroon ako ng direct computation here. So that would be 96 micromolar squared all over second. So that will be the value for the Michelson equation. Yan. Ayan, here. So I forgot pa na meron tayong andito. We have the variable 9.6 kasi nga, ayan o, multiply both sides. So, hindi pa tayo natatapos pala dito. Ayan, 9.6 km or micromolar per second. So, we will indicate the unit here, 9.6 micromolar per second is equals to 96 micromolar squared per second. Ayan. So, ang determine, ayan, no? So, Km, so this will serve as our X. And then after that, yan, we have to multiply both sides by 9.6 micromolar per squared here, and then 9.6 micromolar per squared here. And then, ang mangyayari dito ngayon, this will be, so ma-cancel to, ma-cancel yan here, and ma-cancel ito, ma-cancel yan, ma-cancel to, ma-cancel to. And after that, ang magiging ko natin dito, syempre, the Km value will be 10 micromolar. So that will be our answer or the Michaelis-Menten constant for the reaction of this. So, ayan. Take screenshot, guys, for the calculations. Yan. So that will be our discussion for today. Thank you for listening, and I hope you learned something from this discussion. So, ayan, this is just the overview of our topic for today, and I hope you learned something. So thank you, guys, and goodbye.